Hello students, we are now going to start with the fifth module where you have two chapters in it. One is the limitations of algorithm power and the techniques for the algorithm power. So now what we are going to do here is, now we will be seeing how to cope up with the limitations of this algorithm power. So we are given with basically two techniques. One is your backtracking and another is your branch and bound technique. Okay. So now first we will just see when you say it as the two principal approaches for tackling, we have in the previous class we were talking about the P problems, NP problems, NP hard problems, etc. So we have the combinatorial problems where it is a classification of the generation of the subsets, where we will be seeing it as a NP, we have seen it as a NP hard problems. So these hard problems, there are basically two different approaches for tackling this NP hard problems. One is you use some strategy which will be guaranteeing you for solving the problem exactly, but it will not give you any guarantee for finding a solution which will be in the polynomial time factor. As of now, we have studied, we have learned that any algorithm, if you're given with a problem, we are designing an algorithm by using various techniques. We have seen the decrease and conquer, divide and conquer, dynamic programming, greedy approach, etc., where you will be seeing that whenever you go for any approach, you will be designing an algorithm. We will find out the time complexity. We will compare the algorithms with each other, and then we will be finding a solution with keeping in mind the better or efficient algorithm. So when here, while talking about all these things, we have seen that all these NP hard problems will not guarantee you to find a solution which gives in a polynomial time factor. Mostly it will be of exponential time. Now we are going to use an approximation algorithm which will be finding you a solution which is approximate, or you can say it as a suboptimal in the optimal polynomial time complexity. So here we have various strategies to get the exact solution. You have the SOST search, which we have seen in already in our brute force method, where you will be using these for solving the problems like traveling salesperson problem, knapsack problem, assignment problem, which will be used only for a small instance. The second approach is the dynamic programming, where again it is applicable only to certain problems, like for example the knapsack problem, or finding the shortest distance, or finding the path, etc. Now here we are going to introduce two techniques, that is the backtracking and branch and bound, where it says that in backtracking we will be eliminating some unnecessary cases while you consider all the options. Whichever option doesn't yields a better solution, we will be just eliminating it, or we will be discarding it. So it is going to yield you a solution which will be in a reasonable time for many of the instances. But if you consider the best, average, and the worst case in the three different cases of the time complexity for the efficiency, we may say that it, for the worst case, it will be giving still in the exponential form. So you know, as our input size increases, the time taken will be varying, or it will be increasing. Now, the advantage of branch and bound is it will be further refining the backtracking method or the technique for getting you the optimized solution. So it will also be dealing with the optimization problem. So among the backtracking and branch and bound, we have already completed the brute force dynamic programming. So we are going to see the backtracking and branch and bound, where it says that when you use the backtracking, we are going to find a solution by constructing a state space tree. Now, what do you mean by the state space tree? The state space tree is nothing but it is a tree structure where you will be generating the tree to get a solution. So when you say it as a tree structure, basically we know that in a tree we will be consisting of n number of nodes, as well as there will be various edges also. So now when you consider this nodes, each and every nodes in the state space tree will be giving you a partial solution. Whereas the edges will be saying what is the choice for extending this partial solution. So when you say it as a tree structure, we have seen in our decrease and conquer technique that we have the tree traversals where it will be of two different searches. One is either your breadth first search or your depth first search. So keeping those concepts in mind, we are going to explore the state space tree using the depth first search. So when you say it as a tree structure, for example, you can see here, just I'm giving an state space tree where you will be having n number of nodes will be there, as well as there will be edges. All these nodes will be saying it as a partial solution. All these edges will give you the choices. So you need to now depend upon the development or the exploration of the state space tree using something called as the depth first search. So here we are going to see the backtracking by using depth first search. Now, each node for this tree structure will be considered as a prune or a non-promising node. What do you mean by a non-promising node? That when you traverse the tree structure based on depth first search, it will be stopping the exploration of the tree rooted at a particular node, which will not lead to a solution. In such a case, we will be backtracking to a node's parent to continue the search. For example, let me take this tree structure. In this tree structure, you can see that there are certain nodes which are not explored further. Why these nodes are not explored further is nothing but all these nodes, whichever doesn't leads to a partial solution, we call them as the non-promising or the prune nodes. So whichever solution, partial solution, whichever node says that it is a partial solution, that will be explored further. When you explore the entire tree structure, you may get a single solution or you may get more than one solution. So here we are going to explore the tree structure where you will be finding a solution for any given problem. So here the backtracking will be constructing the state space tree based on the depth search pattern, and it is used for majority of its applications. So for a search, any problem given, the choices are made based on certain constraints. So you need to see whether you are following the constraints. If you find that a particular node violates the problem's constraints, then we will be saying that it will not be constrained and it is called as a non-promising or a prune node. So it is done by constraining all the first remaining options for the next stage. So when you say it as the backtracking method, it will be undoing the last component of the partially built solution and it will be replacing it by the next alternative. So it is basically a convenient method to implement the processing of by constructing a tree where you will be having various choices, and when you generate it, you will be starting with a root node The root node will be representing an initial state before the search for a solution which begins. So the nodes of the first level, whichever it's given, it will be based on the constraints. So first you take your first child, you generate it further. If it doesn't lead to a solution, we call it as a non-promising node. And if it is not leading to a partial solution, this non-promising nodes are called as the dead end, and we need to move backward. We will be going backward to its parent node. We will be generating it further. So when you backtrack it, since you are backtracking it, this is called as the backtracking technique. And as and when a node is generated, if it is found to be a promising node or it gives you a partially constructed solution, then it will be leading to a complete solution. So all the leaf nodes, there will be, in a tree structure, there will be the last level. You can see if there are no more children to be generated, then it is called as a leaf node. We have seen all these terms in our introduction chapter itself, where you are defining what is a tree and what are the various terms or the concepts used for a tree structure. So in a backtracking, if you see that there is a non-promising or a dead end, or you will be getting a complete solution for the leaf node. If the current node is promising, then we will be further generating it by following all the constraints. If the current node turns out to be a non-promising, then it backtracks to the parent node and it will be considering the next possibility. Finally, if the algorithm reaches a complete solution of a problem, it will be stopping it or it will be considering for the next solution. As I told you in the beginning itself, from while you generate the tree structure for a specific problem, there can be a single solution or there can be multiple solutions. So if you generate the entire tree structure, here we have generated only the partial tree to get a first solution. But if you generate the entire tree structure, you will be ending up with various solutions. Maybe there are chances for getting more than one solution. Okay, this is all about your backtracking. So backtracking is nothing but, I will repeat it once again. You have a state space tree where you are going to construct the state space tree where the tree consists of two different things. One is your node and another one is your edges. If you follow for any problem, we are going to follow the depth first search. Depth first search, already we have already seen this. The depth first search is nothing but starting with a root node, complete all the nodes in a particular path. It may end with a leaf node with a solution, or it may lead to a non-promising node. So if it is a non-promising node, you need to backtrack and choose the other paths of its parent node. If there are some other children left out to be tracked, you can track it. So here in this, you can see that in the first node itself, let us assume this is your parent node. If you consider its children, it's a non-promising because maybe the constraints are not satisfied. So when you go for another option, maybe the constraints are satisfied. So this is a partial solution. So we are going further. So each and every node may either end up with a partial solution. When it is a partial solution, you are going further. You are going to moving to the next level to generate its children. If it is a non-promising node, you are backtracking to its parent node and finding out whether any other children are left out to be traced. If any children are left out to be traced, you are moving forward, or else again you will be moving backward, go to its own parent node and find out whether there are any other edges left out. Edges are nothing but it reflects the choices. So from this, by using the backtracking method, it is a convenient method for finding the solution. Is it clear? So now We will move on to some examples given in this technique. The examples given in for the backtracking technique is nothing but the NQN problem. You have the sum of subset problem. You have the Hamiltonian circuit problem. So here, when you say it as the NQN problem, the what do you mean by this problem? First, we need to define the problem for algorithms. When you are given for a problem, we need to first find out how the problem is being defined over here. Only then you will be able to obtain a solution for it. So here the NQN problem is basically nothing but it says that placing all the NQNs on a n by n chessboard. So you are given with a n by n chessboard. In that you are placing the queues in such a way that no two queues attack each other. Basically, what do you mean by no two queues attack each other? It should not be if you are not being attacked, which means that no two queues should be placed in the same column. It should not be placed in the same row. It should not be placed diagonally also. So by default, each queue, if you take queue 1 will be placed in the first row only. If you take the third queue is going to be placed in the third row. But we need to find out how it can be placed in the various columns by not attacking each other. Getting it? So here we are going to take an example as the 4-queue problem, where you will be given with 4 queues and a 4x4 chessboard. We are placing all the 4 queues in such a way that no two queues will attack each other. So next we will move on to the state space tree, where you are going to try to solve this problem, find out the solution. So basically, when you say it as a 4-queue problem, you will be given with a root node. What is the root node? The root node is only the initial status. The initial stage says that it is a 4x4 chessboard, which is an empty chessboard. Now, when you say it as an empty chessboard, we are trying to place the queues in such a way that the queues should not attack each other. And as I told you, the first queue should be placed in the first column. Okay, so we will try out this option first. Either when there is a dead end, you stop it and go backtrack it. Or if you get a partial solution, you try to go further, move forward. Or now, if it is promising node, you are going further. If it's a non-promising node, we are backtracking. So first thing what we will do is, we know by default each and every level you have in a tree. If you see, there will be various levels. Okay, we are not going level by level. We are considering the root node. We are going to extend it with this same path. Okay, till you reach a leaf node with a solution, or till you reach a dead end, which is to be backtracked. So now, when you start up with, by default, we know that the first level is for first queue. The second level is for the second queue. The third level is for third queue. And the fourth level says that it is for the fourth queue or the last queue or the nth queue. Now, when you go for the nth queue, we are saying that we are stopping the process. We just complete it by getting either one solution, or you will be getting more than one solution when you completely track this tree structure. This is your state space tree. When you complete the state space tree, you may get one solution where we can stop it, or we may get more than one solution. So now we will see how to place it. So as I told you, it is a depth first search. So in a depth first search, what we will do, we will start with the first queue, placed it in the first row, first column. Now we have to see, can we place the second queue in the first column? Is it possible? What is the condition? The condition says that no two queues should be placed in the same row, same column, or in the same diagonal position. Diagonally also it should not attack. For example, if I am placing the first queue in the first column, I cannot place the second queue in the first column. Why? Because it is column attack. I cannot place the second queue in the second column. Why? Because it will be diagonally attacking. So you see, for while you are placing the queues, you see to that it is not attacking neither in the column nor in the diagonal position. So for the first queue, if you place the first queue in the first row, first column, is it possible for you to place the second queue in the first column? No. Why? It diagonally, it is the same column. Now try for, since it is a dead end, what you will do? You will be backtracking. Backtracking is nothing but go to the parent node. Is there any other option? Yes. For each node we have 4 options. What are the 4 options? Because it is a 4x4 chessboard, we are left out with 4 columns. If one column is not working, you try for the other 3 columns. Clear? So here we are going back from the parent node. Already the first queue is placed in the first column. So we are going to see how to be placed the queue in the second column. Is it possible? No. As I told you, it should not be in the same column, nor it should also not be diagonal. So when you cannot place it in diagonally, it becomes a dead node or a non-promising node. So we will be moving to the third column. Now, can you just tell me, can you place this in the third column? So can you place it in the third column? No. Just to check, can we place it in the third column? Yes, we are placing it in the third column. Now, when you place this queue in the third column, now what we are doing is, since it is a partial solution, see here, we tried for the first column, it was not possible. We tried for the second child, it is to place in the second column, it is not possible, it is a dead end. Now, for placing the third queue, there is a possibility. So, this is considered to be a partial solution. Since it is a partial solution, we move ahead forward by trying for placing the third queue. So, third queue again, how many options are left out? There are 4 options left out. So, we will just check for placing the third queue. So, when you place the third queue, can you place it in the first column? No, it is not possible column wise. Can you place the third queue in the second column? No, it diagonally attacks. Can you place the third queue in the third column? No, column wise it attacks. Can you place the third queue in the fourth column? No, it is diagonally attacked. So now all the 4 options are dead ends. So when it is a dead end, what we do is we just go back to its parent node. So only 3 3 edges are being completed so far. So we are going to the fourth one. Now when you go for the fourth one, we are trying to place the second queue in the fourth column. So when you try placing the second queue in the fourth column, you just try whether you can place the queues. So placing the queues in the fourth column, we will be checking. First option is third queen has to be placed in the first column. It's possible? No, it will diagonally attack. Can you place the second queen in the third queen in the third column? Yes, it is possible. Since it is possible, this becomes a partial solution. Since it is a partial solution, we are moving forward. So the fourth queen, it is trying to place it in the first column. No, it is not possible because it will diagonally attack each other. Can you place the fourth queen in the second column? No, column wise it will attack. Can you place the fourth queen in the third column? No, diagonally it will attack. Can you place the fourth queen in the fourth column? No, column wise it will attack. So I will repeat it once again. When you place the first queen in the first column, we are trying for the second queen to be placed in the first column. Column wise it will attack. We are trying for placing in the second column. Diagonally it is attacking. We are trying to place it in the third column. Here we get a partial solution. When you get a partial solution, we are going further. We are taking the third queen, trying to place the third queen in the first column. Is it possible? No. Column wise it is attacking. Can you place it in the second column? No. Diagonally it attacks. Can you place it in the third column? No. Column wise it attacks. Can you place it in the fourth column? No. Diagonally it attacks. So you are just going to check for a current queen. When you are going to place it, you need to compare it with all the previous options made. Previous options can be eradicated only if you backtrack, go to its parent and choose another option. So that is why this technique is called as a backtracking technique. So since we are not getting the solution, we have tried for the third column, we have tried placing this third queen in the fourth column, it's not possible. So we are again, all the four options are over. So we need to move to its parent node. In the parent node also, you can see that there were only 4 edges and all the 4 edges are been eliminated. Why? Because all these 4 edges leads to a non-promising node. Since it is leading to a non-promising node, we move backward, we go to its parent node. Again, we will be seeing whether there is any other option. Yes, there are some options left out. Why? Because we tried only for the first child. So now there is a second child, third child, fourth child. So first we will try working out with the second child. The second child indicates that we are going to place the first queen in the second column. So when you place the first queen in the second column, we try for placing the second queen in the first column. Is it possible? No, it is not possible. We try the second queen to be placed in the second column. Is it possible? No, column wise it attacks. Can you place the second queen in the third column? No, diagonally it attacks. Can you place the second queen in the fourth column? Yes, it's possible. Now, since it is possible, this becomes a partial solution. Now, since it is a partial solution, we will be moving forward. Moving forward is nothing but trying to place the third queen in the first column. Can you place the third queen in the first column? Yes, it is possible. So again, this becomes a partial solution. Now, since it is a partial solution, we need to move forward. When you are moving forward, what it says? It says that you are trying for placing the fourth queen. Can you place the fourth queen in the first column? Is it possible? No. Column wise, it is attacking. Can you place the fourth queen in the second column? No. It will diagonally, it will attack. Can you place the third queen in the third column? Yes, it is possible. Here you can see that the each and every queens are placed in such a way that no two queens are in the same column, as well as it is not diagonally also, it is not attacking. If it would have been diagonally attacked, we would have, for example, here you can see it's diagonally attacking, we are not placing it. We say that this node is a prune node or a non-promising node. So here we get the final solution. This is our first solution. We may get another solution also if you still generate all the children. So I am leaving the generation of the entire state space tree to you. You please try out we have worked out for the root node, we have worked out only the first child and the second child. What are the two options left out? You can generate the third child, you can also generate the fourth child. When you generate it further, you may get another solution. The other solution will be that for the 4 by 4 chessboard, it is the transpose of it. Okay, transpose of this first solution will give you the second solution for the NQ problem. Is it clear? Now, when you go for this, we have to write an algorithm. So here you are given with an algorithm for NQ problem. The NQ problem says that we are going to place the 4 queues in a chessboard in such a way that no 2 queues attack each other. So for all the 4 queues, for I equal to 1 to 4, or in general 1 to n, you are going to see whether you will be able to place the queue. So you are going to call an algorithm which is called as place algorithm. What this place algorithm does, it will be checking for all the previous queues placed for the current queue. Can you place it in the same column, whether it is attacking? Can you place it in the diagonal way, whether it is attacking? That has to be checked. So this algorithm basically it returns a value as false or true. False when it is attacking either in the column wise or in the diagonal wise. When it says that it is not attacking each other, then it will be returning a true value. Now, for example, just take this example. Okay, so here we are saying that it is in the previous queue is in the same column, so you cannot place it. Now, go to the next position. What this position indicates in a matrix for a 4 by 4 chessboard, this position indicates that it is third row, second column. So 3 by 3, 2. Now you are going to see whether any other queues are in the previous queues are in the attacking in the same diagonal position. Okay, column wise nothing is there, it's that column is empty, but you need to also check for diagonal. So when you are just checking it, you just check whether it is diagonally attacking. So here you can say that supposing if you have a queue here, how it is showing it as it's diagonally attacking, this is at what place? It is at 2, 3. Okay, the position here represents here in a 4 by 4 chessboard. It indicates that it is the second row, third column. So what is 3, 2? 3, 2 is 1. What is 3 minus 2? It is 1. What is 2 minus 3? 2 minus 3 is minus 1. Whether 1 is equal to minus 1? No, not at all. But the absolute value of 3 minus 2 is equal to the absolute value of 2 minus 3. So absolute value of 1 is 1. Absolute value of minus 1 is also 1. So 1 is equal to 1? Yes. So it is diagonally attacking. Is it clear? For example, here you can see, I will just tell you one more example. Here we can say that the first queue is already placed in the first column. So column wise you cannot place it. But how you will be finding it whether it is attacking diagonally? That is, for example, the first queue is placed at 1, 1. The second queue we are trying to place in the second column. So it says that it is 2, 2. The second queue when you are going to place, it is in the second column. So it is at Second row, second column. So what is 1 minus 1? It is 0. What is 2 minus 2? It is 0. Whether 1 minus 1 is equal to 2 minus 2? Yes, 0 is equal to 0. So which means it is diagonally attacking. Since it is diagonally attacking, we cannot place it in the second column. So we are moving the second queen to the third column. Is it clear? So please, when you are seeing it, you see to that it should not attack column wise, or it should also not attack diagonal wise. So we are checking, if at all, if you want to place a particular queen, you are going to see what is the remaining queens placed previously, whether it is in the same column. Similarly, if you take the absolute value of the placement, you can find if the values are equal, then you can see whether it is at the diagonal position. If either any one of this is true, if it is in the same column or same diagonal position, then you cannot place the queen. Otherwise, you will be able to place the queen. So this algorithm, place of k comma I, it returns with a true or false. If it is returning with a true, then you can place that particular current queen in that position, and you check whether you have placed all the queens. If you have placed all the queens, you get the solution, or else if you are not placed, then you go ahead with the next queen. So for a 4x4 queen, you will be trying to place all the queens in a chessboard in such a way that no two queens attack each other. Is it clear? So we are here, what we are seeing is, we are trying to find out how to place all the queens in a 4x4 chessboard in such a way that no two queens attack each other. So here I will just go through it once again, saying that the backtracking, it constructs the state space tree. So you will be having the nodes and the edges. The node says that it is a partial solution. The edges says that it is the choices for the partial solution. You need to explore. Always remember that for a backtracking, you will be using the depth first search. So there will be certain nodes which are called as the promising nodes and the non-promising nodes. Non-promising nodes are also called as the prune nodes. So these non-promising nodes, what it says is, it is a dead end. You need not go further. You will not get a solution. So we need not generate it further. We will be backtracking, going to a parent node and continue our search. So while you continue the search, you will be seeing whether the search is satisfying your constraints. If the search satisfies the constraints, then we will be saying that it is a partial solution. If it violates the constraints, then we will be saying it is a dead end. So whenever you come across with a dead end, you will not be going further. You will be backtracking it and you will be stopping the process. So stopping is nothing but you are not going to end the process. You will be backtracking, go to its parent node, find out whether there is any other option available. If there is any option available, you will be going further. So this is all about your backtracking and seeing how to place the 4 queens in a 4x4 chessboard. So you will be asked to write a program for finding the placement of all the 4 queens. You use the iterative statement and just get all the various solutions. Or else what you will do, you will be saying that you are going it further and you will be getting either a single solution or all the solutions. So that's all about your NQN problem. So thank you, students. We will meet in the next class with the next topic for the backtracking method. Okay.